the first part of this morning session, and now we're going on to the second part. Before we start, as we go on, you will have questions, I'm sure. So could you write down the questions on a piece of paper and keep the question really brief so that, and clear so that we can ask it easily from here. And have your name, where you come from, which city, which school, and have a question, just as I said, in 2 lines. And please restrict yourself to 1 question per student. Yeah? Thank you. And now we'll get started. We heard in the morning Christianus Langfollard, Carl Hendrik, and Rich Roberts talk about their research experiences and how curiosity drove them to make interesting discoveries. One of the very interesting aspects of science today, as it's grown as an enterprise, is that this curiosity often requires teams, small teams, medium-sized teams, and sometimes very large teams doing work. And there is also a very large number of excellent people in every area. So these 2 things are very important to keep in mind. Teamwork is critical, and therefore multiple components of a project require expertise from several set of people. And therefore, how does one, develop and share the credit for that? And secondly, given the large number of excellent people and the challenges of deciding who's done something first or later, means that often very talented people don't get recognized by the highest awards. And everyone knows that and appreciates that. So it's okay not to get a Nobel Prize. And the Nobel Prize winners also know that. But they are bearing the responsibility not just for communicating the excellence of their work, but for communicating the excellence of their whole field. And once you get the prize, you're asked all sorts of questions on every subject, and it's a huge burden for them to be able to answer everything. Sometimes they say, I don't know, and Serge Haroche has a joke about, I don't know. I'll ask him to say that. But there are answers also to many of these kind of questions. Now today we have with us Serge Haroche, who won the Nobel Prize in Physics, and Tom Lindahl, who won the Nobel Prize in Physiology and Medicine. And both these people have done extraordinary work which has had an enormous impact on their field. We'll hear a little from them about their work, but more to get started, I'd request Serge to tell us a little bit about how he thinks teamwork plays a role in top quality science, and then we'll go on to how we can build those teams and the institutional structures in schools and colleges so that collaboration and teamwork can result in quality science. Serge.
Yes, I would like to say that, of course, doing science and being a researcher is usually not to work alone. Of course, there have been some exceptions. You can think about Einstein doing his big discoveries as he was working in a kind of void. He was not recognized at the time he started. But this is quite an exception, and most of the time when you work in a laboratory, especially if you do experimental work, and you work with a team. And you have students, of course, but not only students, you have collaborators, you have people at the same level as you are, and this is also very helpful to start your work, especially if you work in a new area. It's one thing you should look for is when you ask yourself where do you want to do your research, is to be in the right environment, to work in a place where you will have colleagues who are experts in fields which are slightly different from yours and from which you can learn new techniques, new ways of thinking. And this happened in my case. At some part of my research life, I needed new technologies, and then I could go in other parts of the lab and ask people who knew about this field, and this helped me tremendously. Also, another aspect of the work team has to do with one question which was asked before. What happens when you are at a very difficult stage of your research, when something does not work, when you have the feeling that you are in a dead end, should you get discouraged or should you keep going? And if this happens when you work in a team, it helps tremendously because you get solace from discussing with your colleagues. At this time, to have a good sense of humor also helps because you can make this difficulty look a little bit relative compared to what other bad things which may happen. And also, if you work in a team, it means that you have different projects working together. And if something happens on the main project, and then you could work on what was called bread and butter projects, which were working on the side. And this is particularly important if you train PhD students, because you cannot keep PhD students for 20 years in the lab working on the most ambitious project of your life. You need to have projects which can give results on a shorter time scale. And so you need always to have in mind the fact that even if you pursue a very ambitious long-term goal, that you have some small pieces of the project on the side which will make good PhD works for the students who will have to leave your lab after some time. So, and my experience is working on small-scale teams. I'm talking about groups in which you have 10 to 15, maximum 20 people. You have, of course, some projects in physics which involve huge groups. Working in an accelerator environment means that hundreds of people are working together. Working on big astronomy projects in astrophysics also involves huge teams. And then you have other problems which arise. How do you organize these teams? It means that researchers have to be also entrepreneurs. They should know how to work with large groups, and there is a problem of human relations and also of recognition. Who gets the recognition, and how can you make sure that all the people working will be recognized enough to have a good career in science? And I think this is very important, but I don't have any experience in this domain. I want to add a word about the fact that anyone will not get a Nobel Prize, of course. And there is a good reason for that. When the Nobel Prize was created, was at the beginning of the 20th century, the whole community of researchers were maybe a few hundreds or a few thousand at most. Now you have hundreds of thousands, maybe millions of people doing research, and the number of Nobel Prizes has not changed. It's always at maximum 3 people in a given field each year. So it means that the selection is much harder. It does not mean that the prizes are, that the people who get the prize are brighter now. So I think it's not the case, because from the beginning, and what made the value of the prize, it has been given to fantastic people. But it means that it has become more of a gamble. In my case, I know I'm working in a field where many people are working, and I can quote maybe 10 or 20 people who would have deserved the prize, and then it's a matter of luck, of being chosen a given year for many reasons which have nothing to do with the fact that you are better than your colleagues. And so when you get the prize, you have to recognize that and to decide that you have to become the speaker for a large domain of research, and to talk not only about your work, but about the work in your field, and beyond that, to talk about science in general, as we are doing today.
Thank you very much, Serge. Karl-Henrik Helden, the chairman of the Nobel Foundation, is here, and he might take Serge's suggestion and increase the number of prizes to a few thousand.
I did not suggest that.
Honestly. So, this is really very valuable about how teams are structured. But, you know, one of the interesting aspects of this morning's discussion is the large number of school students who are here today. And these students are coming from all over India. There's a program to select bright students and give them opportunities to visit research institutes. That's the Kishore Vaigyanik Protsahan Yojana. The students are there from that program. And then there's another national program called the Atal Innovation Mission, and that has tinkering labs in schools all over the country. And these labs are meant to allow students to go and play around and you know, do whatever they wish. And the idea is that these labs will interact steadily with research institutions also. So my next question, by the way, I'll come to Tom Lindell soon. Tom has a very, very bad throat. He can barely speak. So there are some questions and themes for him. But when we ask him that, he will whisper that his answer to me, and I will speak it out. But my point, pardon? Yeah. So my question to Serge is there, in terms of building these teams and building enthusiasm for science, is there something we should do from the policy end to have greater interaction at the school level between students and researchers?
I think what you are asking is a very important question, which has to do first with education in general. You need to have, in India and all, not only in India, in all countries of the world, you need to have a good education system, because the population at large need to be trained, especially now that the technology is evolving very fast, and that new jobs will be created which will require new expertise in new fields, new talents, and more than that, we can expect that during the lifespan of the young student now, things will again change. And so the most important point about education is that it should prepare young people to be flexible enough to keep learning during the rest of their lives. So you need really general education. And this is very important for science, because even if most of these people young students will not become scientists themselves, it's very important that the society at large recognize the values of science, because science will be essential to solve the problems which mankind will face. And it is not obvious. We see now, at present time, that there is a resistance against science, that science has some enemies, that there are some values some negative values which are permeating society against science, like the notion of alternative facts, of fake news and so on. And so you need to educate the general public against this, to make science recognized as a universal value, a universal research of truth. And so this is a general part of education. But this involves a huge number of students, and only a small fraction of the students will become scientists. So this education system has to be flexible enough to recognize young talents, to nurture the curiosity that is so important, the passion for science, and to develop at the same time general education for all, and good conditions for young scientists to emerge from that. And what you said about the special training and all what is made in India to try to recognize young talents is very important. But I think beyond that, you should have a much more general approach to science, which will be important for everyone. I think we talked before that about collaboration between people in research teams. But when you are a scientist, in fact, you collaborate at the more profound level with all the generation of scientists who were before you. And this is the history of science. And I think education should insist on that, and you should have a good education about the history of science, how the ideas of science have evolved in time. In my personal life, it has been very important. When I was a young student, I was fascinated by astronomy and by the fact that you can compute the trajectories of planets and find what is the velocity of a satellite. And this happened at the time when the technology was evolving fast, and the time of the first satellite and the race to the moon and so on. But I was really fascinated by the fact that someone like Newton in the 17th century was able to discover mathematical laws which explain that. And this was not only science, it was more generally a cultural perspective, the fact that you have to learn how great scientists have made a difference. And it is at the same level as literature or art or painting. You have to learn about the great cultural advances in the history of mankind, and science is only one aspect of that.
So I think Serge is making a very important point about the value of general education, and science being one component of that, and we'll come back to that. But I'd like to go on a little bit to tell you about Tom Lindahl's work, which has been both working with his team and which has ended up making discoveries in how DNA breaks are repaired. And this has been really vital in both understanding how cancer takes place, how the onset of cancer, but also how to treat cancer by repairing breaks or to causing breaks in cancerous cells and damaging them. And this work has been a fantastic example of how government investment in science has paid off over the long term. Tom studied in what was did his research at what was then called the Imperial Cancer Research Fund, which then became Cancer Research UK, and now has moved to the Francis Crick Institute, which is again an extraordinary example in the UK of the government, the Medical Research Council, private charities such as the Wellcome Trust and Cancer UK, coming together to create a fantastic structure for cancer research. And they have interpreted cancer research to be very broad, to look at everything from how cells are made to do the kinds of multiple tasks they do, how they divide, how they make organisms, and how indeed cancer takes place. I think this is a very extraordinarily successful example of how research can, in biology, because of the shared thread of evolution, looking at one question can result in answers to some other question. And the Crick Institute, as well as the MRC labs, have students coming from everywhere and interacting too during their open days and other examples. So I have a question here for Tom from a student, Stacy, who asks, is cancer a disease or just a deficiency of metabolism, such as vitamins? And is it true for all types of cancers, or is this true for only certain kinds of cancers? So how does metabolism cause or not cause cancer?
Cancer is a disease usually caused by a mutation, and we have to define those mutations.
So cancer is a disease caused by one or more mutations in the cells of our body, soma, and they, can result in the cells proliferating and becoming cancerous. And we need to define those mutations. Now, there are multiple hypotheses which say that you can cause these mutations by metabolic defects, environmental agents, and so on and so forth. But the consequence of a combination of factors funnels into the DNA, and mutations in specific regions of specific genes can result in cancer. So there are many types of cancers, and each one of them is caused by a different set of mutations in different genes. Now, we'll come back to a question which Serge touched about, and this is a very different topic from cancer, and that is from Aryan Rao. By the way, can you stand up, Aryan, if you're there? Just to, there you are, yeah. So Aryan is over here, this side. So Aryan had a question, and the previous question was from Stacy. So Stacy, are you there somewhere? Yeah, thank you for asking that. I should have asked you to stand up earlier. So Aryan, your question, you have two questions. Let's go to the second one, and if we have time, we'll come back to the first. As a scientist, how do you deal with those who have misconceptions and who refuse to accept scientific proof?
I try not to deal with them, but it's an important issue. I think science is based on facts, so you observe nature, and from what you observe, you try to develop theories which explain what you have observed, and these theories predict new facts, new phenomena that were not known before, and you try to observe them, and this is called experiments, And if you observe them, this reinforces the value of your theory, and you learn new facts, and these new facts will lead to eventually to applications, to new technologies, and these new technologies will allow you to develop new devices which will allow you to probe nature more precisely than before, and so you will learn again about nature. And here I am defining a kind of virtuous loop going from observation to theory to technologies and to new observation and so on. And this is a way science builds up knowledge, making knowledge coming from observation and from proof, from demonstrations that what you have been observed is really true and really the facts. And so you define truth as scientific truth, as something which comes from this very well-organized and virtuous system. Now you have, of course, people who don't believe in that. They just have the idea that what they see is true without making any theory. They assume that any opinion is a theory. I'm talking, for instance, about the people who advocate creationism against Darwinism. And this is something which becomes very worrisome in this time. And science is very fragile in front of that, because if you are discussing with people who don't accept the values of science and the way science is building up step by step in the way I've described, there is nothing you can say rationally, because they don't follow the rational reasoning. I think that in the end, science wins, because science has results, and the results of science are all the discoveries, all the devices which have revolutionized our lives during the last century in science, in medicine, in technology, and so on. So eventually science will win, and we have to believe in that. And it has happened in the past. In the 17th century, when Galileo tried to put forward the ideas of Copernicus about the fact that it was the Earth was moving around the Sun and not the opposite, the Pope was against Galileo, and eventually Galileo won over the Pope. And in the 19th century, when Darwin put forward the evolution theory, a lot of people were against it, and a lot of people are still against it now, but it's clear that the evolution theory is winning because it explains things and it led to all the revolution we know in biology. And I am sure that science today we have some politician who say that some words should be censored. Trump has said that the word scientifically proven should not be used anymore in any reports from the NSF. Yes. So this is of course absurd, and I am sure that science will prevail over Trump after some time. So we have to be hopeful, we have to be optimistic about that. Science has been proved, not only the result of science, but the scientific mind, the scientific way of doing things has proved to be successful over the last centuries, and I'm sure it will again overcome this negative and this strange attitude. I'm very much surprised that now, at the beginning of the 21st century, we still have to face these kind of problems, but this is the way it is, and we have to deal with them.
So I'll ask Tom a question about how this debate between scientific views, which are constantly, self-questioning, self-correcting, and views in different sections of society about science, and communicating science. How is that dealt with in the UK, for example? There's a very robust science communication program. People like Brian Cox are, communicating by radio, television, in public areas. Are they effective, or are they just another kind of evangelist? Just as you have evangelists giving different kinds of views, has science also become evangelical rather than being participatory with the public?
In Europe, most people believe in science, and if you're a young person, it's important that you're not misguided and that you believe in experimental science. It's difficult to sit in front of a computer all day and do important work. Real progress, quantum leap of knowledge, often comes from unexpected observations. And you have to be smart enough to realize that this was not just due to your own technical mistake, but something new. Don't put it aside, but pursue. Why wasn't the result coming out the way you expected? The answer is very simple. Nature is still smarter than you are, but you should do your best to be as smart as science as nature.
So the important point about science and communication is that we need to communicate that scientists are not people sitting in front of computer screens and, imagining things. They, interact with the society around them, with other scientists, and they're constantly questioning, and they make mistakes. And when they make mistakes, they ask, why did that happen? I didn't expect this to happen. And when they, realize that something new has happened, then they make discoveries. And this process is what needs to be more widely communicated. Now, the important other point, which Tom said right at the beginning, was this process, all of us in society, as we grow older, we have opinions. And those opinions may or may not agree with facts. And we are entitled to our opinions. There's no problem in that, no matter how, weird they are. But we are not entitled to our facts. And when we as policymakers have opinions, we should be very careful in implementing those opinions in school education programs, for example, because during school, when you're growing up, you need to be given a set of mechanisms to question and understand, and not arbitrary viewpoints coming in which change day by day. And Serge's example of the history of scientific views and how they were opposed is an example of how long it takes for views to come in. But the foundational training needs to be robust and strong, so that as you grow older, you can choose whether to accept it or not, question it, and have your own opinions. But at least you understand what the scientific method is. I'll go on now to a question which has come from Raghav Sharma, which is related to a recent discovery which got the Nobel Prize last year. This is the Laser Interferometric Gravitational Observatory, which detected gravitational waves for the first time. So I'll request Serge to tell us a little bit about gravitational waves. But I'd also like to say that India is a very proud participant in this. Kip Thorne, who got the Nobel Prize, was here in January a few weeks ago. And India is one of the 3 experimental stations for LIGO, the Laser Interferometric Gravitational Observatory. So the Indian site is coming up. And Indian scientists, Vishweshwara at the Raman Institute 30 years ago, who worked with John Archibald Wheeler, who was a famous gravitational scientist, Vishweshwara made important predictions which were tested out and used in this discovery, and Kip Thorne talked about that. There were also current in the detection of the gravitational waves in those experiments. About at least 60 Indian scientists were there, and all these scientists, along with those others in LIGO, 1,000 of them, got the Millennium Prize. The Millennium Prize, unlike the Nobel Prize, has no limit to the number of people getting the prize. So I think they got a few dollars each, but it was a recognition for their work. So with that, I'll ask Serge then, what does it mean for science that gravitational waves are detected by LIGO for the first time?
I think this is a fantastic example of many issues we discussed yesterday and today. First of all, it's a curiosity-driven project. It's clear that detecting gravitational waves has no direct effect on any application, on any useful things we could benefit on in our everyday life. It's a discovery of waves which had been predicted by Einstein in his theory of general relativity in 1916. Einstein, working on Newton's ideas about gravitation, understood that there was something missing in the way Newton described gravitation. The fact that, according to Newton's idea, when gravitation was due to the direct force between masses at arbitrary distances from each other, and according to Newton, the effect was instantaneous. There was no time lapse between the time a mass appeared somewhere in the universe and the effect it had on another mass. And Einstein found that there was something wrong with that, and that gravitation could not propagate faster than light, according to his special theory of relativity. And so he developed a new theory in which gravitation was due to the fact that a mass placed somewhere in the universe changed the shape of space around it, and not only the shape, the way space was behaving around the mass, but also how time was elapsing. And he described a theory in which the masses were changing the shape of space and time, and other masses around experienced that and moved in a different way because space, the shape of space has been changed. And so if you start from this idea, if something happens, if a mass changes at a given point, it makes a ripple on space-time which propagates the speed of light through the universe, and these were gravitational waves. And for many, many years, for about 1 century, people have computed what should the effect of this ripple be, and it was a very, very tiny effect, and for a very long time it was supposed that it would never be observable. The effect which was predicted is that if you take, let's say, a length of a few kilometers and measure the distance between 2 points in one direction and then in the orthogonal direction, the passing of a gravitational wave should shrink the distance on one arm and expand the distance on the other arm. But the difference is so tiny that you can not even grasp what it means. The difference in this distance should be less than 1 billionth of the size of an atom. The size of an atom is about 1 billionth smaller than the size of microscopic objects. And so to go from our size to the size of one atom, you have a factor of more than 1 billion. And to go from the size of an atom to the distance which was moved by this gravitational wave was another factor of 1 billion. And to be able to detect that was supposed to be absolutely impossible. Until about 30 years ago, when some people have started to think that using lasers, one would be able to do that by making a very, very precise interferometric measurement. And I know one of my colleagues I was working with when I was a postdoc back in the 1970s and 80s in France had this idea which was starting to be discussed everywhere by the people who were going to develop LIGO and Virgo in Europe. And it was like a dream, and it took them 30 years of development to fight all causes of errors, and eventually this project was successful 1 or 2 years ago, and this proves that basic science is really a long-term project, and it has to be supported in a very constant way, and it has to have the trust of the people who give the money. And this was a successful project in the United States, in Europe, and in other countries. It's a very important collaborative project. So I want also to say that it's a fantastic discovery because it puts together two very different orders of magnitude. First of all, the very tiny effect on Earth, which was supposed to be absolutely undetectable, very, very small effect. And this has to be compared with the cataclysmic phenomenon which produced it. The first detection was a detection of the collapse of two black holes, which were start to rotate around each other faster and faster, and when it reached a velocity close to the velocity of light, it collapsed, and it gave a propagation of this gravitational wave. A lot of energy was produced. In fact, you cannot imagine the energy. 3 solar masses have disappeared in the process, and 3 masses equivalent to the mass of the sun. Now look at the sun itself. The sun is producing all the energy we have on Earth to live and to heat our planet and so on. And the energy which reaches our planet is a very tiny part of the energy of the sun. And the energy of the sun corresponds to 1/1,000 mass of the sun. So a very tiny part of fraction of the mass of the sun, and it disappears in 5 billion years, about the duration of the sun. Now, we are not talking about 1/1,000 of the mass, we are talking about 3 solar masses, and we are not talking about 5 billion years, we are talking about 1 second. This happens in about 1 second. So you cannot imagine the order of magnitude of this huge phenomenon which occurred somewhere in space and which produced such a tiny effect on Earth. And this is a fantastic illustration of the power of the human mind, that the brain of people on Earth, on a small planet somewhere in the universe, were able to conceive all this and were able to produce the instrument which was able to observe this. Now, this is basic science, and this will have tremendous consequences in the future, because these gravitational waves are a new kind of information we get from the universe. Up to now, most of the information came from electromagnetic waves, from light and from radio and microwaves. Now we have gravitational waves, which are completely different and which give us other kind of information, especially about black holes and neutron stars. Another important lesson we get from that is the idea of being lucky. One did not know at all how many of these events occurred in the universe. And during the first few weeks, maybe the first few days when LIGO was working, they observed the first event, which means that these events should be rather frequent in the universe. And when Virgo started working last summer, again, a few events were observed. And this means that there are a lot of events like that occurring around, that we learn a lot about the way the universe is working by combining the information we get from gravitational waves from what we get from electromagnetic radiation. And again, this is something which will have no direct implication, except for the fact that we are developing new instruments which might be useful for other purposes. For example, the lasers which are used in these antennas have fantastic properties, and they may be used for other applications in the future.
Thank you very much, Serge. I should add 2 points. One is every Indian mother and father seems to want their kids to become engineers or doctors. And in the case of LIGO, the advances in engineering and technology helped greatly in a theory which was proposed decades ago to allow the construction of instruments along with physicists to detect. So it's not such a bad thing being an engineer. So they're very bad. So big teams need that. Yeah. Serge, would you like to comment on that in terms of how these teams are managed?
Yeah, I don't know very much about the management of the team itself, but I think it's very important to have scientists who have a vision of what they want to achieve and what are the fundamental ideas behind. In this case, it was just to demonstrate, to find, to observe a phenomenon which had been predicted very long ago by Einstein, and which is essential to understand the way our universe is working, to a very broad view of the cosmology of the universe. And on the other hand, to achieve that, you need very refined technology and instruments, and for that, engineers are very important. I was lucky last summer to visit in France, in Lyon. There is a lab which is inside the University of Lyon, which has produced all the mirrors of LIGO and Virgo. And these mirrors are a fantastic achievement, a tour de force achievement. These are mirrors which are something like 50 centimeters in diameter, and which are polished with a precision which of the order of nanometers of the size of an atom. Any defect on the surface of the mirror would scatter light in the wrong direction, and they are also coated by a special coating which makes them extremely good reflectors of light. And the development of these mirrors is an engineering feat, and without these mirrors, LIGO and Virgo would not have worked. So all this, it's not only the 1,000 people who got the prize that you were talking about, but the thousands of technicians and engineers working throughout the world which have been very important for this discovery. And you not only need to be good at building lasers and mirrors to reflect lasers, you have to be extremely good also to avoid vibrations. So all these mirrors are suspended on very thin threads of quartz, which makes these mirrors impervious to the vibration of the Earth, to the fact that you have small tides and tremors due to very small earthquakes, which were not sensitive at all to here in our daily lives, but which become very detrimental if you want to observe the tiny effect I was discussing. And all this is again a tour de force, and it requires the expertise of specialists in mechanics and mechanical engineering to build these devices. And really, I think if you study that in detail, it's a fantastic illustration of the power of technology at the service of basic science.
Thank you, Serge. I should add that those of you who are interested, and by the way, I'm getting a lot of questions on physics, interestingly. Those of you who are interested, Kip Thorne, who was one of the recipients of the Nobel Prize last year for LEGO, gave a wonderful lecture at the International Center for Theoretical Studies in Bangalore recently. And that's available on the net. And that is a very good public lecture about LEGO. And there was also very nice YouTube clips explaining gravitational waves. I saw some of those on Twitter, and I had a competition for people to translate that into Indian languages, and two won the prize, one in Kannada and one in Marathi. So if you would like to take on Kip Thorne's lecture as school students and get your teachers and other scientists to translate the text is also available. That will allow this to reach a wider audience. Now, let me...
I may add also, since we are the Nobel series dialogue here, that you can find the Nobel lectures on the internet too, and the three winners of the Nobel Prize give different aspects of their discovery in the Nobel lecture.
So that, for you all to see those lectures, the Nobel Facebook site, for example, has millions of viewers every day, a very large, I think the greatest number are from India, but those of you who go there and enjoy it should also try to see whether you want to communicate that to a larger set of people. Let me move briefly, we'll come back to physics, most of these questions are on physics. Let me move briefly to Tom. Tom, you mentioned cancer being a disease caused by mutations. Now, there are a wide variety of tools now available to sequence the entire genomes of various cancers. And this has gone on, the International Cancer Genome Consortium has gone on for some years now. But here, from the perspective of school students, since those kinds of data are available, would it be something valuable for them, just as you have people looking up through a telescope and looking at the skies and seeing the data, seeing the skies and seeing what's happening. And today you can get radio telescope data which is accessible for them to look at. Shouldn't there be a way by which school students look at this kind of a data and reach their own conclusions? Maybe something interesting will come out of them.
Yes, but it's important not just to repeat the previous work and sit and look in a telescope on what is known already. You have always to try to think, what can I contribute, even if it's a small part.
So, Tom's very important point is that, when you look at the skies, you look quite often at what others have already seen. But the huge value in looking at cancer genome data, for example, or such kind of data, is you're just not looking again and again at the raw data, but you can distill it, analyze it, and reach your conclusions. And that's something, again, in terms of computer science interest, which many people in India have an inclination to, but also allows you to do cutting-edge science right at your laptop in your schools or colleges to analyze this data in your own way. So don't just look at that data, but question it and see what you can derive from that. Now, back to physics, Serge. I hope you've had a short break. Here's a By the way, the previous question, I should have said, the legal question, I should acknowledge the person who asked the question. I'll find that paper. Yes, that was Vandana. Can you stand up? Yeah, thank you, Vandana, for asking that. Yeah. Now, the next question is from Kabir Nayak. Where's Kabir? There he is. Kabir wants to know that the universe is expanding. That's true, he says, but where is the mass being created for that expansion? Or is there mass being created at all as it expands?
Okay, there is another thing we did not discuss here about scientists. They don't know everything. And I am not a specialist in cosmology, so I could not discuss these ideas. Of course, cosmologists are learning a lot of things about the origin of the universe, the expansion of the universe, the fact that there was an early phase of what they call inflation, in which the universe expanded extremely fast during the first nanoseconds or microseconds of the universe existence. And we get information about that mainly by detecting the cosmologic background radiation, the microwave which is permeating all universe and which comes from the early stage of its existence. It's clear that during this phase, quantum effects were important. The quantum fluctuations were essential to understand what's happening then. But for that, you need to ask a question for cosmologists, specialists of the early phase of the universe. A guy like Kip Thorne is maybe somebody who could answer this question. I don't want to give answers because I don't know.
Would you like to, at this stage, tell them the joke you told me about I don't know?
Oh, yes, it's a story about the way you have to try to train children to be curious about things. We have been said that the children always ask questions at the beginning of their lives, and this is a curiosity which is obvious in young kids. And the story is about a father who is walking in outside in the street with his child, and the child keeps asking questions. He says, "Dad, why does the moon appear to be bigger when it is near the horizon and not the height of the sky?" And the father says, "I don't know." And then the child asks another question, "Why is the moon going around, I have learned that the moon is going around the earth, why don't we see it moving in the sky all the time? We don't see this motion." And the father says, "I don't know." And the child keeps asking questions. Each time the father is saying, "I don't know." After a while, they keep walking, and the child is silent, does not say anything. And the father turns to the child and says, "Why are you not asking questions? Keep asking questions. How will you learn something if you don't ask questions?" So this is a story about giving answer to children, and also the fact that you should not trust all the time the answer that you get if you get one.
So there are different ways of saying I don't know. You can say I don't know, or you can say this is what we know and this is why we don't know, or this is why I don't know. And that requires a lot of effort on the part of the teachers or the parents also. Here's a question, Tom, back to a biology question from Manasi Pitre. Manasi? I can't see her. Maybe she asked a question and ran away. Oh, there she is, right at the back. Yeah. Hi, Manasi. So, Manasi asked a question about, vaccines and diseases. Some diseases are treatable by vaccines, preventable by vaccines. Smallpox is a great example, polio, and others, even against cancers. There are some vaccines coming up now. Cancer immunotherapy is very valuable, and human papillomavirus caused cancers are treatable by vaccines. But why is there no vaccine for other diseases such as AIDS and malaria? Is there something wrong with the way the scientists are looking at these questions? Are they not looking at it enough? Why don't we have vaccines against AIDS, malaria, tuberculosis yet, which are effective?
There are certainly many attempts to develop such vaccines, but the immune response is not perfect. It recognizes some things very well, but if it's an altered cell that is rather similar to its progeny or precursor cell, it can be difficult to define that difference. And the immune response isn't effective enough to deal with it.
So the history of vaccine development was amazing in that attempts to just take inactive or poorly active virus, for example, inject that and raise an immune response was very effective for some diseases. So the fact that smallpox was started early on was extraordinarily lucky. And if, instead of smallpox we were trying to develop a vaccine against AIDS as the first one, it would have been very difficult. So many vaccines turned out to be there because of being fortuitous of choosing those diseases. Other diseases, as Tom pointed out, are such that the parasite or the virus or the bacteria either hides itself in a manner so that there isn't a sufficient immune response. And it's very difficult to develop a vaccine which exposes the immune system to the parasite, but at the same time is then effective when actual infection occurs. Other diseases like HIV/AIDS, the virus will reconfigure the immune system so that its response is poor. So these are very difficult challenges which people are taking approaches. HIV/AIDS, by the way, even though the vaccine hasn't been developed, retroviral drugs which affect the virus have been developed, and an Indian company, Cipla, is the world's largest producer of generic drugs against HIV/AIDS and has saved, millions of people around the world. Serge, you wanted to say something on that?
About vaccines, of course I'm not a specialist at all, but I must say that it is also an example of some reaction against vaccination, are an example of the anti-scientific trends that we were talking about before. I think it's amazing in view of the success of vaccination to eradicate some disease in the world, that there are some people who are against vaccination. There are some resistance in France among some part of the population which says that the vaccines are not good, and they are propagating false information about that. And I think it's a problem which we have to face, because if some parents don't want their children to be vaccinated, it not only they endanger their own children, but I think they endanger also the general population, because diseases which had disappeared might come back if the population is not protected against it.
Absolutely. I think this moves very nicely into the next question from Spurti. Spurti, where are you? Yeah, thank you for asking this question. Spurti's question is about science in the internet age. Everyone's connected, they get access to facts of different kinds, and there's equal time given to facts and other kinds of fake news. How does one deal with this from a community effect? How do school students, how are they to choose between what is right or what is wrong, which area to explore, when if you Google a particular topic, you have 10 different viewpoints coming up?
I think it's a very serious problem which goes beyond science. It's true that you have a lot of stupid things or a lot of lies which are propagated in science, but also in other topics, in politics, in general, in history, negating things which have happened in the past. And the problem is it's very difficult to fight against that, because the people who read this news tend to build into small communities in which they propagate the same news and they reinforce their beliefs because they just listen and read what they want to read about. And the question how you fight against that is a very difficult one, because science operates along different lines with different ways of building the truth. And if you have to fight people who don't accept the rules, it's very difficult. You just have to, again, you just have to hope that if you have a good education, young people will be able to recognize facts from falsehood, will be able to recognize the fact that all what you read is not true, and that you have to use your critical judgment to decide what should be trusted and what should be proved and is not proven by just what you read.
Thank you, sir. Tom?
That is a great role for good teachers here. If you're a teacher, you have a big responsibility to teach the next generation the right things, scientifically correct things, and not some myths or religious beliefs. You have to deal with facts. Even if you don't like them yourself, you have to deal with facts. And that's what the next generation needs, understanding.
So, Tom's critical point is that in this internet age, Spurti's question, the role for teachers is very, very important. They have to convey facts in a manner which is robust, even if they don't believe in it. There was a very beautiful essay by an Indian poet, A.K. Ramanujan, and he used to write his poetry in Kannada, English, and Tamil. And he used to look at his father, who was a mathematics teacher, working on number theory, and his father was also a very religious person. And he said he was impressed by the way his father compartmentalized his mathematics teaching and his belief in other systems, which strangely included the use of mathematics in astrology. So he asked his father, why is it that you go to class and teach number theory, and how is it that you also believe in astrology? Isn't this strange? And Ramanujan was puzzled by this. And his father replied that he understands this contradiction, but when he goes to class to teach mathematics, that's what he does. He's got other beliefs, and that's his business. And this kind of a mechanism by which, an individual here is managing contradictory beliefs. It's much more complex in society where there are hugely contradictory beliefs there, and somehow occupying the middle ground where reason is used in science and not clouded and mixed up with other areas is critical. And there, teachers again and students like you have a very important role. Now, I'll go into a more physics question again. This is from Mandakini. Can you stand up? So Mandakini has a question which is on electromagnetism, and she says an accelerating charge will produce magnetic waves. So why doesn't that happen in an electron circulating around the nucleus?
Okay, so this is, we are coming to quantum physics.
And she asked actually that how does one reconcile quantum mechanics with classical physics?
Okay, I could talk for hours on this topic. That's true that electromagnetic waves are produced by atoms which are made of charged particles and of electrons circling the nucleus. According to classical physics, an electron which is accelerating around the nucleus should radiate continuously and eventually fall on the nucleus. So if you accept classical physics, matter would not be stable. And this was one of the big puzzles at the end of the 19th century. Maxwell had discovered the law of electromagnetism, the way electric charge radiate, and something was wrong at the atomic level. Then, at the beginning of the 20th century, Niels Bohr came and he gave a planetary description of the atom with a caveat. He says, on some stable orbits, the electron is not radiating. On the ground state of atoms, the electron on a stable orbit is not radiating. If you excite the atom to an excited orbit, it will eventually radiate and emit a quantum of light, which later was called the photon. So it described a quantum world in which the electromagnetic phenomena, which was supposed to be continuous according to Maxwell, became discontinuous, gave rise to quantum jumps and to a completely new way of looking at things. Einstein understood that Bohr had discovered some part of the reality, but Einstein did not like at all this idea of quanta, of discontinuous behavior of nature, of randomness, because the photons are emitted at random times. But he did not like it, and this comes back to earlier question we were asking. He did not like it, but he was forced to it by the fact that it described the observed world. So in spite of the fact that he did not like it, he eventually had to accept it. And this is part of the big difference between beliefs and science. Einstein was a great scientist because he had to accept even things that he did not like. We talked before about the fact that scientists have something to do with a detective. We observe some facts and we have to deduce from these facts a theory. Einstein did that, and he was like a detective who finds that the criminal belongs to his family. He does not like the idea, but he has to accept it as a fact, and that was a part of, I would say not a tragedy, but a part of the difficulties Einstein had to face during his life. He had to accept facts in spite of the fact that he did not like the way they behaved.
So there are a huge number of other questions, and unfortunately we're running really out of time, so we have to stop. The questions are really fantastic. We will have them sent so that they are put up on the internet and all of you can look at it and answer. And you know, the students here have been really fantastic in asking these questions. I would urge you to go and visit the Nobel Media Facebook page, and also very importantly, after the session, the next session is with the teachers. During that, please visit the exhibition and please visit the